So we're trying to implement the Softmax multinomial diversity regression theory. Well, and so we went through some of these ideas. So there is a Softmax function to be universally used in machine learning, let's say. And so the idea is that this takes a vector and gives this raises each entry to the raises e to each entry and then normalize it. So it produces probably vector out of any vector that you give it, and so it's shift invariant in the sense that if I add a constant shift, it's not going to change the output. Okay? So the input changes, but the output doesn't change, and mathematically verified. And so the building block was this linear kind of layer, or linear model, and it stands for neural networks, and it's like a submodule of this PyTorch. So PyTorch NN import as NN. Now I can use NN dot the classes that are defined in there. So, and then the linear is a predefined class. It implements a linear function, or actually an affine function, which has a weight increase and a bias circular. So let's say 2 features and output 3 features. So the matrix would be 3 by 2. So the input dimension. So we define the number of columns in the output dimension number of rows. So this matrix is multiplied by each input. The 2-dimensional equates a 3-dimensional vector. And then this vector is added to the output. So the bias is added. So that's the bias, it's the weight. Yeah, so we went through the mechanics of this a little bit. And so the way that you apply it to a vector is just to apply this function. So this mean object that I created is now like an object that I can treat it as a function. So yeah, so this is really a function. I mean, it's an object, but it behaves like a function. So when I apply it to x, it does function evaluation. So it evaluates that function over each row of x. So this is again a convention. PyTorch that the rows, or the first dimension, which is the 0th dimension, is always representing the samples. Okay, so each sample here they have the vector, which is 1 minus 2, 1, 0, and then 0, 1. So it operates separately in each row. Okay, separately in each row. And so you would get a 3 by 1. In this case, it would be 3 by 1. This is like 3 by 2. So the output would be 3 by 1, which is the function applied. Let's call this L. So if this is x1, this is x2, this is x3, then you get L of x1, L of x2, L of x3. Okay, so that's the output. Dimension is 3 by 1. Oh. Why is not 3 by 1? So this takes 2, 2, 3. So it would be like 3. Each one is going to be 3-dimensional. 3 by 3. Right? So maps 2 dimensions to 3 dimensions. So this says okay. Sounds good. Does that make sense? Everyone understand how this works? This is basically the building block. The simplest model is like the linear model, or you want a mathematical affine model. Affine means this added intercept.
So what is this 3 by 3 again?
So this takes 2-dimensional features out of 3-dimensional vector. Okay, so when you apply to each of the rows, you get a three-dimensional vector, just put in the rows. Right, so the input is like 3 by 2. Then it gives me like 3 rows because this is 3. Each of the rows will be 3-dimensional.
What would you go to from R2 to R3?
Why would I go? It's just an example.
Okay.
I can go to R4, for example. Let's say if I do 4, let's say I do 5. So input dimension 2, output dimension 5, and I can instantiate this to kind of populate these ways and bias automatically at random. So you can check the documentation, most likely generates from a normal distribution. So you can see now it's like 5 by 2 because the output dimension is 5 and the bias is also 5. Right, and then if I apply it to, so let's not do this because here I'm assuming 2, 3. So what will happen if I now apply it here? What do you think the dimension is? So this is again a 3 by 2 vector. That's imagery. My linear map maps 2 to 5. So what will be the output dimension? 3 by 5. Yeah. So each one of the rows is like the output of that linear map on one of the rows. Okay. So it's a very useful convention because you can have a complicated model, but then you can apply it to multiple samples in parallel. So that as long as you're putting the samples in the 0 dimension.
So usually when we are in the examples we have seen so far, we would try to go from a higher to like the one.
Right, right. So we'll see, like in more complicated models, you could go, yeah, that all depends. So for example, that in the example that we saw, right? Like the Softmax regression, right? So the idea is that the input is d-dimensional. In this case, it's 2-dimensional, right? But here the output would be the number of classes. Okay. So it would be R to the C, right? So if I have the binary classification, C would be 2, but if I perform like class by 5 classes, right, that would be, so it would be 2 to 5, right? So that would be the Softmax idea, right? So it's like the model is S theta times X, Y coordinate, so that would be the probability of Y equal Y given. So this would be C by
The weights and the intercept are random here, right?
yeah, both of them are random. So both the intercept, what they call it, bias, and the weight. Right.
Why is it useful for them to be random?
Why do you think it's useful? So because we instantiate these models and want to fit them, so this acts as the initialization. So you do raise in the second because your initial guess is correct. If you don't have a good guess, usually the random initialization is a good guess. In this particular case, because I want to have a real model, so I actually generated it, and then I populated the. So you can see I set the data of these to what I want. I have a linear model with these particular weights. Okay, so you can't assign these portions and be like the weight because there's a tensor is a parameter, but the data portion is the tensor. So that's one way to do it. Okay, so this is 3 by 3. This is going to be 3 by 4, right?
Okay, another way of doing it is I can apply forward, and also this notation is good. So when you apply it with one index, so if X is a tensor, one index is just takes that row. Okay, given it's like that, I don't know, 3 by 4 or 1 by 5 times 7, right? So this is like 0, the indices are 0, 1, 2. So the 2 would be the second, the last row here, but it would be like 1 by 4 by 5. Actually, I think it would be just 4 by 5. Let's check. So x2, that shape, yeah, it just extracts. In this case, it would be just this, and it would be like a 2-dimensional vector. It just loses the trivial dimension, which would be 1. So you apply this, like right forward. So forward is forward, and does the job, and so you apply lim to x, it's the same as lim dot forward. So it just does that function, and this also verifies that this is exactly the same thing that we expect to happen. So that's my Softmax model. So it's fast. So it derives from the inner module. So it has all the properties. There's this usually initialization, and then this forward. So the initialization sets up the model. The object gets like the property linear, which is the linear layer. A linear map that is independent of dependent specified, and you have the forward. In this forward, basically calculate the value of the function. The value of the function in this case is apply linear to x and apply Softmax on the dimension 1, which is along this dimension. Okay, so you take that this matrix, which is going to be we'll do it with 3. So this would give me so you have, for example, n by d, you have samples, and this goes through this, you get n by c. So each one is like, so this, for example, is like x transpose. This is like x transpose, theta transpose. And then you apply Softmax. Okay, because everything is like on the rows, it's like the other way around. So this is the column oriented, this is forward. But like intuitively, you apply a linear map to this, and then you apply Softmax to get the probability. So that's how this works. So if I apply, for example, let's say, okay, I have to create the model first. So we create the Softmax model with 2 inputs, 4 outputs. So I'm taking up the 4-class classification. And then you can list the parameters. That's how you do it. And also multiplying by 5. So I can loop through the parameters. These are my true model, multiply by 5. So this multiplication by 5, you want to remember what it does. Multiply by 10. Yeah, so this will control the level of the noise and problems. Okay. Makes the boundary structure less structured. So the higher the value of theta is, you can see that the Softmax pushes to these in the context of like binary classification, when you push towards these areas where it gets saturated, the labels become more deterministic. And so if things are large, they're most likely end up here, and so you have more. The probability of observing a specific class is more crisp, and so the difference between the actual thing that you observe is smaller, so the noise is lower. So that's my true model, and yeah, so I can apply. You can see I can apply. I generate X as a random, like a basically Gaussian. So the X, the I entry, so the I throw is normal to the variance identity. So now I have a matrix that is n by 2,
normal distributed, they apply a true model to apply to each row and using the probability. So when you plot it or create it, is going to be first side is 2004. And then each row here, you can see sums to 1, and it's a probability observed different classes for that input. Okay, so it's a 0.88 here. Just these two classes are high, the rest. So I can probably maybe torch. See if this works.
Just round.
Yeah, round works. No, I want to do this. So I don't want to do that. So let's see. Understands round 2 decimal points. Okay. Oh, not that. I just want to print it. So there's no digits. No, it's still like, okay, so you can see like roughly 1, this is like 87.11.2. This one will be a little bit easier to see. So 0.6, 0.1, 0.3, 0.3, 0.7. And so on. Okay, so each row is a problem. Okay. So that's so what do I do if I want to like find the Bayes rule? Like this is a true model. So what would be the Bayes classifier in this case? For example, what do you find in this input? So that X corresponding to this row and this set of problems, these are the problems. So what is the Bayes classifier is assignment classifier? Argmax. The Argmax along this line, which would be it would be like this point. So that's the class tree, 0, 1, 2, 3. Here would be 0. So okay, so if I do argmax, basically, torch argmax probability dimension 1. I should vote. I think this as well. Right, so the first one in tree, a little more random. So let's change that. Class 0, class 0, class 3, and so on. Yeah, yeah. Class 0, class 2, okay, 2 is like this is another 13.5.5. And move back around probably the around. Okay, so these are the Bayes labels. Okay, the difference between these optimal labels and the actual label. So what is the actual label? The actual label is when I generate. So I'm not generating yet from the label. What I would want to do is once I have these probabilities, I'm going to generate from these probabilities and like a categorical value. So that's what we did here. So these are the true labels. So you sample from the categorical distribution with these probabilities, then you get the labels. So every time you do it, you get different labels. So that's the noise process. Okay, so the fact that the this is the probability, but every time you generate, I get a different set of labels. So I generate one, so I get a set of labels. These are true labels. These are not necessarily going to match the Bayes label or Bayes optimal label. And the difference is the noise that captures the noise. So that's the true Y. And this is the Bayes sort of classifier Y. So these are the optimal, my optimal rule. These are and then they sort of match here in this case because there's less noise. And then I'm gonna plot these and so
These are the y class of the page rule. And these are the two labels. Let's see,
the decision boundaries are very clear when you do that.
is,
So far, so good. Okay, and then so fitting. So we didn't do this last time.
so I'm gonna like introduce a little bit more of these, so machinery and approach. So we wrote our own gradient descent, but you can also do it
with this prepackaged SGD from the optimization one.
So towards the optim dot, you have a bunch of options, SGD one. And stands for stochastic gradient descent. I'll talk a little bit about the stochastic, but you can treat it as gradient descent. So you pass it the model parameters. And then the learning rate, and you can pass it the it's 0. And
See what I did here. Actually, I don't need the optimization at this point. Maybe later. Okay, so
let's have that in mind. And then I define the loss, which is called my loss of here the model. I'm going to evaluate the model, whatever the model is. Currently, you do the probability from the logs, the log of the probabilities. So what this is doing is,
what are we doing here?
what I'm doing here is calculating basically this one. I'm going to calculate this. So how do I do it? I'm just basically gonna say I'm gonna so this is gonna for us the probability matrix. So for the ith entry, I'm gonna pick yi. Okay, because so that's like the so I'm gonna have this. Right, I'm gonna calculate that. So for each row, I have xi, and then I have yi. So this is gonna be that probability matrix. So probability matrix, the ith row. Wait, so data xi. So these are gonna be my different rows, basically, if you want. And so what I'm gonna do is for each row, for the ith row, I'm gonna take the yi column. Right, so that gives me the probability of observing that particular label. So the range in train is like 1 up or 0 up to n-1, so that's the index I. And then corresponding to that, I have the y, which is like basically I'm forming this matrix, I and yi. So I have a matrix which has this form.
Okay, so let's see if that's maybe. This is gonna work. Not easy to do, but I'm not sure if this is gonna work. This is not a tensor. Maybe this is good. Tensor. Okay, so this gives you the idea.
It's the other way around. These are the I, and then these are the y.
Okay. So I'm going to index like this into the probability.
So that would give me the likelihood, the log likelihood. Right. So the likelihood is what is the probability that there's a particular yi under this model. So that selects the probability that the model predicts on for this label. And so this is really the log likelihood. And it's the negative would be negative log likelihood average. So it's like 1 over n summation. That's the empirical sort of
Risk idea, right? So that's my loss. And okay, so this gives like
just reminds you what. So is there any question about the loss?
Right, I'm basically calculating this one. 1/n summation I from 1 to n. Negative log s eta x I y I. So that's the basically probability model for the I. So that's the vector of size C. Tells me which probability is the different classes for this xi under the model, and I'm going to take that y element, which is the probability of observing the specific yi. What is this? This is calculating loss. My current model. So I have a true model, and I instantiated like a new model. This is going to be. This is not the one that generated the data. So there's this true model that generated the data. So this is the generative process that I designed, right? So remember, there's this true model that we initiated, okay? And this true model has a certain set of ways, actually random in this case. But they set the seed, so you can do manual seed. So this fixes a particular random seed so that this model is going to be having a certain set of weights, although it's random. So that's my true model. From the true model, so I generated X and then sampled the Y's from the true model. Right, so these Y's correspond to the true model. So it's just generated from the true model. This model here that I created, this is just again create a softmax regression model with random weights. So this has nothing to do with the original, like the true model. But I'm going to try to fit it. I'm going to try to fit the data. See, because the data is random from the same model, I'm hoping that if I fit the same model, then I get a good result. Okay, so this model is going to be our like working model or estimation model or estimated function model. Okay. But the one that we want to estimate, initialize at random. So should hopefully understand that there are parameters there. When I instantiate the model, parameters are random. And if I just predict now, it's going to be bad. So maybe we can predict. So let's I'm going to show you. But okay, so maybe do this. So let's say if I do model X. So you can see the predictions are sort of all over the place. So these are probably, and so roughly all the classes get equal probability, which is not bad. So for initial guess, initially we don't have any specific notion. So if you randomly change hopefully like either close to like 140. Okay, so that's the initial prediction of the model. The true model is not like this yet, right? So it's true if you do true model. True model is very crisp, okay? Because of the way that we constructed. So that's the prediction of the model. So I'm going to fit this. So let's do. First, I'm going to maybe like evaluate the loss. So I have the loss of the model. So this loss I'm going to measure which relates between x and y. And then here I'm creating the parameters of the model, main parameters. So the name of the parameters and the gradient of the parameters. So I loop through the like the parameters and the gradient, and then I do this loss backward. And then I print the parameters and the gradient of the parameters. So the point here is to remind you what this does. So this procedure do. Loss that backward. So loss is what I create from applying this function to the model. Okay, so that's my loss. And then I evaluate this loss by passing the model to it and then move loss backward. What would happen? A lot of things happen in the background.
To construct the gradient.
Right, it goes like once I create, then I create this loss in this function. It's a bunch of like Python operations on vectors that you don't even see because they're inside this model. Okay, so the model has a bunch of parameters, right? So there's this linear layer and then
linear layer has weights and biases. So those are parameters, as I mentioned. And those parameters have the gradient property that requires them set to true by default. Again, maybe not obvious, but so that means that PyTorch is going to track the gradient, track like assume that we want gradients with respect to those parameters, and then when you calculate this, it's gonna calculate the nonlinear mapping or whatever mapping from those parameters to this, and then I do this, and all the mappings go all to this, and then all the way down to this. So this is a complicated function. So this function of this data, and actually in this case it would be something like WXI plus D. So this loss would be a function of W and D. And so it has this notion of this functional form. So when I say, so this will be my loss. So when I evaluate the loss, and I do this backward, it calculates the gradient with respect to W. So I get the gradient of F with respect to W, and the gradient of F with respect to D, and all the other parameters that I asked to keep the track the gradient, which in this case just these. Okay. Because all this happens in the background, it might be obvious, but so this is the idea. So when I calculate like run this, first it just outputs the value of the loss, which is like 1.9, and then creates the gradient. Originally there's no gradient, so the gradient parameter. So the graph property of each parameter is none. Once I do this, you can see I'm fitting the same graph of parameters, the graph like the property is populated. So the weights, this is the gradient of the loss with respect to this weight, which would be of the same shape. And the gradient would be of the same shape as the parameter. And this is the gradient of the loss with respect to the bias. Okay. So that's the mechanics of gradient. So you have the model. You map the model to a loss. So this is like a complicated function that computes the loss of the models on the training data. And then I do this loss dot backward and this propagates, like they call it backward propagation, back propagation. For a reason which we don't need to worry about, but this gradient calculation is called back propagation traditionally. Because it goes backward from the loss to the inputs. And it's basically application of the chain rule. The chain rule of gradient, like you know the chain rule, right? So if I have like a couple of functions. If I want to calculate let's say the derivative with respect to W, what is going to be like this? These are scalars. Well, it's going to be the derivative, like G prime, right? Like something like a G prime of this, and then F prime of GW. Right. So this operation happens inside. So for example, this is a composition. It wants to take the gradient. It goes in, so the gradient passes this, and then passes. You know how to take the gradient of the log, right? So you take the derivative of this times the derivative of the log, which is like 1 over. So you know how to do this, and how to do this, and how to do this. So just the application of the chain rule of differentiation, and the fact that the individual operations knows how to take the gradient. This is this backward operation. So back propagation, if you heard, it's just calculate the gradient in this like manner. You don't have to worry too much about it. It's just calculus. Calculus. Sometimes called automatic gradient, like differentiation autograph. So it's a nice way of automatically differentiating functional forms that we generate. So far, so good. I guess you create the loss, you do the backward. This basically gives you the gradient. Now I have the gradient, I can just take the gradient instead. Okay, so my initial parameter minus learning rate times this gradient is the new parameter. I then calculate the loss. Do the loss backward, the new gradient, and then so that's, for example, very simple gradients. So model linear rate minus 0.2, that's the learning rate times model linear rate dot graph. I can move like this is like a bare bones gradient descent. It's 1/7 of the gradient descent. And I'm showing you here
So that's how now you remember the reason why I did this. So this is SGD, corrected learning rate 0.2. So I want to show you what exactly that does. So this is our own gradient descent. Okay. Waves minus 0.2 times the graph. So I calculate the gradient. I take a step in the direction of negative gradient, step sign 0.2. The same here. The same goes if I do up and down the step. Okay. So magically, what it does is it does this and it updates the parameters of the model. So if I create the parameters of the model, after I do this, I get the same behavior. So you can see this is our own gradient descent on the parameters, and this is what this opt-in.step does. Okay. How does it know what parameters to update? It knows because you have given the parameters of the model here. Okay, so when you initialize this opt-in object, you give it the parameter that you want to update, and so this optimizer does not compute the gradient. Okay. So you do the gradient by doing the loss backward. So the gradients are now populated. This does something with the gradient. So in the case of a gradient descent, simple gradient descent is zero momentum, and learning in 0.2, it just moves in the direction of the gradient. That is steps like. So this operation, as you can see, opt-in.step is exactly the same as doing this on the parameters of the model, except that here I'm not updating the parameters, just creating them. This one updates the parameters, now creating the new parameters. You can see that they're the same. So you can look at this a little bit. See if you understand any questions. This just introduces some Python machinery, which will hopefully simplify your life if you understand what you're doing. If you don't understand this, it's very magical because you do loss backward, opt-in.step, and done. Okay. But it's not clear what's going on. There's a lot going on behind the scenes. Okay, so this optimization step does not do gradient calculation. It just takes one step in a complicated fashion. So if I have momentum, I do something else, for example. If I have a more fancier optimization, it does something more with the gradient. But the assumption is that by this point, the gradients have been calculated and they're in the grand property of the parameters of interest. And this just takes one step in there. And this, because SGD is simple, it takes one step in the direction of the gradient. Okay. Sounds good. Yes.
Should you have to clear the gradient after you do the step or it automatically clears?
No, it doesn't clear. Yeah. So if I do it again, it tries to add that. So this doesn't change the gradient. The backward does the gradient. So if you don't clear, when you do loss backward, first in this case, it's going to give you an error because you have it in updates. So you try to run the machinery backward at the same position. I think it's going to give you an error. Try to see if in this case, it's fortunately give you some error that so trying to backward through the graphs for a second time or directly accessing. So this is not sort of allowed for hopefully good reason, but in practice what you want to do is you update the parameters and then you do calculate the loss, you do the backward. It does not clear your grade, so it's just accumulated. So you have to do clearing yourself. You either go to all the parameters that the gradient is zero by hand, or this optimization has this property zero grad. Opting that zero grad just zeroes out the gradient, all the parameters it's tracked. So that's what we're going to do. So if you go here, this is basically my short gradient descent in Python language. So we initialize the optimization. Having learning rates more than zero, number of steps. This just keeps track of the loss history, it just keeps track of the loss. And then I have main loop, which is for each iteration, and then 0 up to number of steps -1. I calculate the loss. I do the backward. So this is my current model. Passing through this calculates the loss of the current model. Does the loss backward, we populate the gradients of all the parameters. Do the optimization step. We move in the direction of the
gradient, so at this point, the parameters of the model have been updated, so I have a new model. Okay, and then I do update the zero grad, so the zero is out the gradient of the parameters that's being tracked. Next time in the loop, I'm calculating the loss, I do the backward to get the new gradient. And the direction gradient. So this is it's implemented, yes.
What is zero grad?
So zero grad, zero is out the gradient of the parameters. So we have the parameters, right? Remember this part. So what does this loss backward do? Originally there are no grants, like grants are zero, like now. I do once, so I get the grad property. You can see the parameters have grad property. For example, the mean, the grade, the grad. So that has a gradient property that gets populated. So if I don't zero out this gradient, next time when I calculate, it's gonna just add up to this. Which is not what I want. I want the gradient at the current location, not the sum of the gradients of all the past steps. So this is the design, the way that's designed. Okay. The
Some of the
design.
gradients is momentum with momentum equal to 1.
That would be roughly like that, yes. Which we don't want to do. Yeah, that would be effectively like this. I think it's designed for a different reason. So for example, you might want to just add up the gradient across samples, for example, and multiple samples. But the gradient of this loss with respect to different samples is added. Right? So I can evaluate the model on different samples, right? And every time I calculate the gradient, I can add up the gradient. So that would be like the gradient of the sum, basically. It's designed for a different feature. Okay. But yes, you're right. I think it would be equivalent to, if you don't zero it out, you make like gradient and momentum.
By zeroing it, you're reinitializing it to 0.
Yeah, you set it equal to 0, so you get the new gradient.
Okay, then you add it to 0.
Then we do our own like a step, right? So you don't want this to like, that would be like a very not a very like interesting way of doing momentum. It's like hidden here. So you want they almost always want to do like that. Because that's how you want to do it. You want to do your steps your own, yeah.
There's also dot forward function, right?
Dot forward. So dot forward is so what does the so there's the backward. The backward is calculating gradient. Dot forward is what does it do? Right? Just evaluates the function here. So for example, if this model, I have the model. So I showed you here. So this is, I have the model. So it has, these models have a forward pass. So this is like implicit when I do ling applied to something, it's applying this like, basically evaluating that forward function. Forward just calculates the function. So this is like neural net terminology, I'll talk about it. So forward is like moving things from the input to the output. So input, you give the input, the evaluating function is like passing this through the function, you get something at the output. Gradient calculation is like backward. So you start from this, you like a backward propagation through the network. But like the mechanics are not that important. It's just functional evaluation, gradient calculation. Mathematically, that's what it is. Okay. Sounds good. Forward, backward algorithm. They used to call this like, forward, backward algorithm, the back propagation. Basically, gradient descent was called this in learning community. For historical reasons or like schematic reasons, you can think of forward, backward. But if you don't want to worry too much, it's just math. Sounds good. So this is implementing our, so let me initialize. Maybe run because I run it multiple times. I want to do, from here. Let's initialize. Plot. Okay, now when I run this, this is gradient descent without momentum. And you can see the loss like nicely goes down after it happens. And what I'm having here, I'm gonna like print the weights. These are the true weights. These are the predicted weights. And you can see there is discrepancy. But surprisingly, if we calculate, so this is calculating past predictions on the ones, the actual training one. So these are the base labels. So these are the true labels. And the error or the accuracy basically between the base labels and the observed ones is 0.85. And the ones, so sorry, 84 actually. This is the true model. This is my estimated model. This is my true model. And they're very close actually. The estimated model is doing better than the base. That's right. Of the rate for off. The predictions are good. Okay. Sorry, let me see. We have. Yeah, what was that? Yes.
By weight, you mean the data matrix, right?
Data, yes. So there are issues with the data. The one issue is like it's not identifiable. So even if you perfectly recover the model, you could get a theta which is different, right? Remember, theta is not identifiable. What does that mean?
With two different values, data we get the same value.
Two different values of theta would give you the same exact probability model. In this case, if I add like a constant vector to each row, so it could be like all the rows are shifted. So when you compare, it's not obvious to when I, for example, show you these two, it's not obvious a priori this is bad because it potentially can shift. So for example, I can do look at the difference of this, and if the difference of this is like a difference every basically row is constant, or basically I want to add a constant to every row to get it close to this. So let's say look at the difference of these and then add that to the other rows. Okay, then it would be a little bit more clear comparison. It's all that you do. But let's see another example, like with momentum. I'm going to do momentum 0.9. You can see it's much sharper decay, but it's like there's a level, it doesn't go below. It's not going to be zero. And so
Because of the inherent point.
there's noise, yes. Yes.
That's the reason it's not going to.
There's the two things. Why? Because there is a noise in the problem, and there's like a finite sample size. So there is the fundamental limit of the problem. If you have infinite amount of the infinite sample size, okay, there's inherent noise, but there is also like this finite sample issue. So if you have 2,000 samples, okay, so let me show you this. Maybe I'll show you later that. So this is the predictions. They're actually like similar. Momentum gives you, right? So you can see the weights are actually better. Now I think the weights are a little bit closer. Maybe this one close to that. Go a little off. But the interesting, the prediction is good. So the prediction matches sort of that. What you'd expect from the true model. Sorry, from the base. Yeah, so why doesn't it go to 0? Okay, so let's do 0.9. So this is roughly, say print final value. So I print the final value of loss is 0.269. The initial value is somewhere around, you can see, 1.8 or something. So for example, if I do 200 samples, right? What do we get? Actually, lots is better. Interesting. Counterintuitive. So, is this ability actually?
I think I'm normalizing the loss, so it shouldn't be a problem with that. Well, 200 samples. These are the labels. These are the days. Okay, counterintuitive. Okay, I mean, necessarily works. It's doing better. So we reduce it further. 20 samples. Okay. See if we can kill it. Oh, it's very better. Okay. So I'll post this, you guys figure out.
I think it's also very separable.
Okay, so yeah,
The boundary points are not allowed.
okay. So maybe, okay, let's do another experiment. 3000. Is it gonna be worse? So this is always like surprising things happen in these like classification problems. So everyone analyzes the regression problem. What was the last? Yeah, so this is like, there's a limit here. But I'll let you figure out why you can do better. Sort of. But roughly speaking, if you have smaller sample sizes, it should be harder to predict.
Because that 1/n sigma law is not.
So there is noise in this, so compared to the population level, right? So you would expect to be able to, generally when you have finite samples, you don't see enough of the model, right? That's the problem. So in this case, it's an interesting question why you can do better. But maybe if you, for example, I don't know, this is like a good, as we mentioned, separation. So maybe if I do increase the, like decrease the noise. So this is very noisy. So let's see what we get. Okay, so that's like the limit is like what, 1.2. Okay, 42 is the best I can do accuracy wise. So let's now maybe reduce it to see like 100. So, and still 1.2, which is pretty nice. Still the same, okay. 10 samples. Let's see. It should fail at some point, otherwise. Okay, it's even better. Okay, this is a very interesting counterintuitive. So it's like prediction. So this is better because why is this better? I know why it's better. Anyone knows why this is better?
I think you do the 10 samples many times and then you take the average over that. You should get.
No, the issue is like I'm doing it all with the training data. So what I'm doing here is I'm plotting the training loss. This is prediction mission of the thing. And if you have few samples, you're gonna overfit. So your loss is gonna go down. So if you maybe post it as homework problem. Generate an independent sample, like test sample, and evaluate it on test sample. Hopefully this goes away. Okay, so you're doing better for your training data. Right? So accidentally, I never did like you can do train test split, but because you have the generating model, so you have the generation model here, which is so we are like generating from the model ourselves. So you can generate excess and you have the true model. Just generate an independent sample and evaluate on that sample, not anything. So this is a very good like exercise in overfitting. Okay. So your loss is going down, you're happy, everything is good, but potentially my guess is that if you just hopefully if machine learning otherwise would be very easy. So if you do that in the test, then you evaluate on the test, it would show you problems. Okay, but generally speaking, yeah, so there is noise and there is a limit which you can't go beyond. Basically, there's a fundamental limit in the problem and also the issue with the samples. But this is a very nice sort of illustration of why you have to worry about overfitting. Sounds good. Okay, a very great exercise here in real machine learning. What else? Okay, so now maybe let's go back in. So always verify and test data, okay, so that this doesn't happen. So let's do. Okay, so the noise is too high, so let's go up. I'm gonna. Where do we do the? Okay, multiply by 10 then. Relatively good set of noise. Okay, we have this. Goes down to that. Thanks. Okay, now I just want to mention something about that. SGD part. So SGD, the idea is that they don't have to, because this empirical risk, this is an empirical risk. And if you go back to the original discussion of empirical risk, the general framework, you're just averaging, you're approximating the expectation with an average, okay, which by the law of large number converges to the truth, and also like expectation is the same, so it's unbiased, an unbiased estimate of the true risk. And so if I just average over a smaller sample, it gives me the same kind of unbiasedness. It will have more variance, but it's still an unbiased estimate of the risk. And because I just want to take a step in the direction of the gradient, I'm not trying to like maybe optimize it perfectly. Maybe I get a slightly noisy gradient, it's still fine. So maybe it still points into the right direction. But the idea of SGD is that I can drop like that. I don't have to evaluate this on the whole sample because that would be costly. Let's say you have 15,000 images. And maybe I'm going to pick a batch of size 64, and I'm just evaluating this average on the 64. Next time I can compute the gradient, I take a random sample again. So every time I calculate the gradient, I evaluate this loss on a different batch of data. And so hopefully as I move along, I'll see all the data, but each time it's a different subset. And I get a more noisy movement, and it might help like avoid like hitting like bad local minimum stuff because I'm moving noisily. So I might be able to. So the properties are very interesting. A lot of people are for data trying to kind of like the SVD. So the stochastic part is basically this stochastic nature. It's like the same thing, but doing it on a smaller subset of the data. And it's like this, the SGD originally, I think the original SGD is when you just take one sample. Instead of this averaging, just pick one sample that would be unbiased, but it's like a very high variance. So just evaluate the gradient on one sample, next time another sample. So that's the stochastic gradient descent. The one that I mentioned is something called mini batch gradient descent, or mini batch is GD or something like that. We don't have to worry too much about the naming. It's just that the idea, like the extreme case, is traditionally associated probably with the who came up with about the name. That's the way things. This idea of stochastic approximation. One row. But anyway, so if I want to do that, I can basically rough and loss. So I change my loss function to rough loss. So what this is doing is that takes a random integer between 0 and n. So it just takes. So these are the indices of the training data, and I'm creating a vector batch size. So batch size is 100 here. So I'm randomly picking 100 of the samples, and this potentially can also like take duplicate samples, which you can try to avoid. But this is like
the statisticians are okay with that. You know, heard about the idea of bootstrapping, it's okay, duplicate it. But if you want, you can take a sample without without replace. This is potentially an example of replace of 100. Data points around 100, let's select this is notation, if you remember, with one bracket, just select the sample. So this selects all those samples in X and all the samples in Y, those are now my new X and Y. Then I apply the model to this new X. And I calculate the loss. And that's it. So this just calculates the loss over like the subset. So it would be like 1 over the size S and then I S. Where the size of S is the batch size, which is 1. Okay. So now if I do the same thing here, you can see what will happen. So this is a very noisy gradient, but it still go down. Okay, it still go down, but there's this extra variance that you see, which also can be used to quantify the uncertainty in your estimate, maybe. Okay, so there's this final loss, which is 32. I think it's the same, about the same. Yeah, okay, within the tolerance. But you can see it's much noisier and just fluctuates. Because I'm keeping the different, let's say I'm doing a different gradient, there's a gradient in different samples, it's not gonna like converge like, to, it's not a problem, right? Okay. The gradient is not gonna be perfect, then something like that. But this is a CD and you can see it works, sort of. And it's much easier to implement because I'm evaluating this, it's much faster, if you see, I mean, maybe. So let's do maybe 1,000, you can see how much it takes. If I do 1,000 steps, okay, so this is that. If I do 1,000 step here. So you see, I can calculate much faster. It's like roughly the same kind of, or I don't think I'm evaluating it, but you can just go and maybe evaluate this, see like the performance. What is the performance? Yeah, performance roughly the same. Oh. Okay, so that's the idea. So for example, if I just maybe my rough loss. So if I, okay, I'm doing it with 200. If I pass, for example, 20, I'll see it's much more problematic or like noisy, but like the prediction, like this is the error of the train, be more fair. So this is not a good video. So I'm doing it on the accuracy of the train. Do it on the test state and here. But you can see the effect, right? 100 less variance, 200 was less variance, and then 500 even less, and then 1,000. This is at this point is very close to the number of samples that we have. So this is the variance. Okay. So now you know about SGD, mini batch SGD, batch size means the size of the sample that it takes to calculate the losses and gradient. Very common in machine learning. Good. So you've seen like in logistic regression, the decision boundary is basically a line or a hyperplane. In the softmax, it would be like the intersection of a bunch of lines. So these would define the potential classes. So classes would be polyhedral, or in this case, it would be like this hyperplane. But what if I have a more interesting like decision boundary that looks like this? You have seen this something like that in the breast cancer data. You find at the level sense that's very often breast cancer, it becomes like carrot. in that case, the linear boundary also does good, but maybe like a non-linear boundary does better.
And like the worst case, the more interesting case, for example, is like if there's one class is inside this circle, the other class is outside. Okay, this is very far from linear classification. So if I try to classify this with my linear decision boundaries, you can have faith. Drastic. So what is the solution? There are different ways to deal with this. One is to naturally extend the linear models to these cases by moving to higher stakes. So this idea of feature maps or like basis functions, etc. But the feature maps, basically you map your data into a bigger space. In the bigger space, the classes look like linearly separable. So this is a very powerful idea. And this leads to the idea of the kernel methods and things like that. The other idea is to just introduce nonlinearity in this, the original domain by just changing this function from linear to nonlinear. So it's like a parametric function theta. I just design a new function. So replace, let's say theta x with a nonlinear parametric model. For example, neural networks. Okay, so neural networks are an actual extension of this idea. We add a bunch of like low-cost nonlinearities, and then you cascade these linear models with low-cost nonlinearities, and you can introduce like complicated nonlinearity. So next time we're going to come back and talk about this. So this idea is like composing linear functions with, let's say scalar nonlinearities. So it's a composition of functions. Composition of nonlinear functions give you more nonlinear. And this is what current machine learning basically runs on, like these large models that you see that we call AI. They're basically all variants of this work. And we can also talk about this if you have time. We'll come back to do this. So we're going to start next time with this. And if we manage to go far, I'm going to talk about language models a little bit because they're naturally tied to this and softmax regression. And it's a good example. We can have time to talk about like some modern models. Okay, sounds good. Okay, thank you guys. See you next time. Thank you.